So 6.3 summation notation. So the idea with this is that if we create more rectangles, we get a more precise area. So I'm going to write that down just to remind ourselves that as we increase, in, which means more rectangles, we get closer to the actual area. So in other words, if I was to start off with n equals 1, so one rectangle using a left Riemann sum, I would have a rectangle that looked like this. Okay, and if I found the area of this, I would be not only covering parts of the area that I wanted, but also parts of the area that I do not want. Okay, and to show you, since we're using -1 to 6, we're talking about this whole section here. Okay, this section here, and this section here. Okay, that would be from -1 to 6. So again, if I was to draw that rectangle, notice how it is covering a lot of blank space. Okay. So if I was to increase this, and let's say n equals 2. Okay, let's say I had a rectangle here and a rectangle here. I'm covering more of the space with a little bit of less of the part that I don't want, but it's still not going to be as precise if we were to increase the number of rectangles. Okay, so if I'm going to assume n is approaching infinity, that means I'm going to have infinitely number of rectangles to approximate this area. And what that would look like is me drawing all of these rectangles to follow the area under the curve and above the curve here. Okay, so imagine all those lines are hundreds and thousands of rectangles, right? So eventually, if we were to use this method with n approaching infinity, we would get a precise area for -1 to 6. However, it would take a long time if we had to calculate the area of each of the rectangles and add them together. Okay, so that is where we start bringing in summation notation. So before we start there, we're going to look at two different ways to also express that as n is increasing, the area is getting more efficient. So the first one says, if n is the number of subintervals on the closed interval a to b, what is the width of each subinterval? So when we talked about width yesterday, what did we do with the two endpoints on the interval? We subtracted them. So what we did is we said that b minus a, okay, to get that distance, and then we divided it by what? N, whatever n was, okay? This is called the change in x. And if I had a rectangle, that would represent that part of the rectangle. Okay, the change in x. Okay, or the width. That's what we called it yesterday, the width. Okay. Another way to think of this, it says if n is approaching infinity on the closed interval, what does the width of each subinterval approach? Okay, so if we think of this, when we looked at yesterday, as n increased, what happened to the width? It decreased. So if we have n approaching infinity, eventually the width is going to approach 0. Okay, so another way is to say, okay, the change in x approaches 0. Okay. I'm over here. Thank you. Is Tristan here? I don't. Okay. Okay, so if we were to take this and then actually write it as a sum of all the areas of the rectangles, we would be taking the change in x, the width, and multiplying it by the height, or the value plugged into the function. So it would look like the change in x sub 1 times f of x sub 1 plus the change in x sub 2, f of x sub 2, all the way to infinity. So that would be the change in x sub n, f of x sub n, where one of these is equivalent to the area of one triangle. However, this goes back to us saying, would you want to calculate the area of 1,000 triangles and add them all together? That's going to take a very long time. So instead of writing it like this, where we're adding up all the areas, that is where the summation notation comes into play. So it says the area under the curve of f of x on the closed interval a to b is represented by the limit as n approaches infinity of the summation of k equals 1 to n of b minus a over n, so the change in x, the width, times f of a plus b minus a over n times k, and that is representing the height. So I have the width and the height. Makes sense? We have to multiply those two things together in order to get the area of a rectangle. So this is taking the width, the change in x, times f of a plus the change of x, k. And in the bottom here, it says n is representing our subintervals, okay, and k is representing the kth subinterval. So since this is n approaching infinity, they don't want to confuse you by using another n, so they just change the variable to k. Okay, k is just standing for the kth subinterval. So think of it as that subinterval increasing to infinity. They're just giving that a name, k. Another way that you could write this to make it a little bit easier to read is the limit of the change in x approaches 0 of the summation of k equals 1 to n of the change in x times f of x sub k. Okay. However, you would just have to remember that equation for the change in x, the width. You'd have to remember that it's the interval subtracting, so b minus a divided by n. Okay. Any questions so far? Yes?
You use k as a subscript for x there, but are you multiplied by k, or is that also a subscript?
That is being multiplied by k. Yes, that's being multiplied by k. And Tristan, this is for you. Okay. So now let's take the summation notation and see how this can translate to integral notation. So it says the limit as n approaches infinity of the summation, so everything we just wrote to the other side, is equivalent to writing the integral from a to b of f of x dx. Okay, f of x dx. So remember, I said to think of this like the definition of a derivative. When we learned how to find the derivative using limits, it's kind of the same thing. Okay, it's showing you how we can use the limit of a summation to find the integral. So for the rest of these notes, all it's having us practice is switching between the two forms. So switching between Riemann sum to summation, summation to integral, and vice versa. So in the first example, it says rewrite the definite integral using the summation notation. So the first thing we have to establish here is what is A and what is B. So what is A? 2. Ooh, is it 2 or 3? 2. Right, because our integral, look back up here at our formula, is from A to B. Okay, so 2 is A. What is B? 6. And then what is our function here? X squared minus 3. Because remember, for the integral, it was f of x times dx, which means that entire thing in front has to be the function. Okay, so this entire thing is the function. So knowing that, we can now plug in what we know into the summation notation. So starting off, we have the limit as n approaches infinity. Again, we don't know n here. Of the summation of k equals 1 to n times, and then remember our formula is b minus a. So what is going to be b minus a? 6 minus 2, so 6 minus 2 over n. And then our next part of our formula is f of, so I'm going to go back here so you can see right here, f of a plus the change in x times k. So that means we're going to take this entire portion of our equation here and plug it in to our function, which we said was x squared minus 3. Okay, so this is going to become 2 plus 6 minus 2 over n times k squared minus 3. Okay, what we did is we went back up to the formula, and where there was an a, we placed a 2. Okay, where there was 6 minus 2 was that b minus a. And then what we did is, since that whole thing is representing x, so this whole thing is representing x, and our equation was x squared minus 3, I went ahead and squared that entire thing and then subtracted 3. Okay, so this is us going from an integral to summation notation. Any questions?
Wait, can you explain what just happened again with that second part? Or like what you
Yes. So remember, our formula is this. So it is a plus b minus a over n times k. Well, a we know is 2. So that's where I plug the 2 in here. Okay, b minus a over n, we already did that in the first part. So that's where this part came. And then the k just came down. All of that is going to represent x. So think of this as f of x. That entire thing is x.
Okay.
So then I plug that into my function, and since it's x squared, I squared all of that, and then minus 3 at the end.
Okay.
Okay, so on the next one, it says rewrite the summation notation expression as a definite integral. So now we're going in reverse. And the reason why it says A, B, and C is because there's multiple ways that you can write this, and it still is correct. Okay, I am only going to show you 2 of the ways because we're going to learn the third way when we talk about the properties of integrals. So I'm not going to do anything in part C. So here we have the limit as n is approaching infinity of the summation of k equals 1 to n. And then we have this first part here. This is the first important part. Remember, that part of the formula is b minus a. So that 6 right there is telling us that we have an interval that contains a distance of 6. Because we don't know what b is, and we don't necessarily know what a is. Okay, so I'm going to write that off to the side. This is saying the distance between the interval Okay, and it's always going to be that first part over n. Because remember, n is just representing our subintervals, which are number of rectangles. Okay, so the very first way we could think of this is we could use the definition, and in the definition it says f of a plus b minus a over n times k. Okay, so I'm talking about, again, that second part of the formula up here. Okay, well, if we follow that, it technically gives us a. What would be a in that case? 4. Okay, so if we're using that original definition, we're going to say a is 4. Okay, so if I'm writing my integral, I know a is 4, and what would b be if I know the distance in the interval has to go up 6? 10. Okay, so I have an integral from 4 to 10, which means that this entire thing here, based off of the definition, is going to represent x. So my function in this case is going to be x squared. And then I always end it with dx. Okay, that is one way to represent this as an integral. And again, this is where we are representing x as 4 plus 10 minus 4. That's how we get the 6 over n times k squared. That is what that function is representing directly from that summation here. Okay. However, we can also assume that instead of 4 being a, like it says in the formula, what if 4 was a part of the original function? Okay. So if we say that, if we assume that 4 is part of the original function, and that means we don't know anything about a and we don't know anything about b, except that there's a distance of 6, we can start our integral at 0. And so now a is 0, and we can go up to 6, so b is 6. Okay, if we are assuming 4 is part of our function, that means our function is no longer x squared, but what? Good. Okay, x squared plus 4, I would keep it all in the parentheses just like it has up there. So instead of saying that, what about 4 plus? Okay, you could also, okay. Yes, I'm thinking more directly. I'm just going to bring it down like this, like 4 plus x squared. But yes, you could simplify that to x squared plus 16. But just so you can see where it's coming from, it's coming directly from this, which means if 4 is part of that function, the only part that's representing an x is the 6k over n. And then, of course, we would end it with dx. So again, this x right here is representing 0 plus 6 minus 0 over n times k. Okay, that is where a is 0, b is 6, and that's how we're able to assume 4 is part of the original function. So these type of problems are not typically problems that they're going to ask you to solve by hand. It's going to be a multiple choice type problem, and you have to see which integral fits best. Okay, so maybe you don't see the integral from 4 to 10 there. You have to know that it can also be written as the integral of 0 to 6 like we did in the second part. Okay. If you had to choose which one is the best though, it would be this one. Okay, because that one makes the most logical sense, right? Because we look back at the formula and we say, okay, that number that is in front of the 6k over n has to be a. Okay, so that would be the best one. And it is also the most common. So I would star it, let's say most common or best. Okay, not to say that the other one is not correct. It's correct. Okay, there is a third way, but again, I don't want to add any other confusion. We'll talk about that when we do properties of integrals. Okay. Any questions on 2? Okay, number 3. Number 3 gives us a limit, and it says, assuming the lower limit a is 0, write a definite integral that represents the above expression. Okay, so now we're not able to choose our a value. It is given to us, and they said our a value is 0. So writing my integral, I know it has to start with 0. Okay. If I look up at the expression, I'm going to pay attention to only this first part here because it says 2 over n. And I know that top portion is representing what? That distance in the interval, right? So if it's going to have to be a distance of 2, that means my b value has to be 2 because it started at 0, so it has to be 2. Okay. Now, if you look at the rest of the equations that are being added together here, notice that the only thing that changes is this part. So we have 2 over n, 4 over n, 6 over n, and then all the way to the end. Okay? Since that's the only thing that's changing, we're going to let that represent x, which means that the function we're looking at is what? 1 over x plus 3. And then we always end it with dx. Okay, so again, we decided to call that portion x because that is the only part that is changing. Remember when we talk about width in the beginning, we call that the change in x. Okay, so x went from 2 over n, 4 over n, 6 over n, etc. Okay, we can just call it x, simplify it to put it in that integral notation. Okay, any questions on 3?
So we called it x because it's changing.
It's the only part that is changing. So if we look at number 4, okay, one thing you should notice is different here is that we know our n value. We know how many subintervals that we're given. And what would that be? 10. Because remember, if you look at this one, this had a number over n. We didn't know n. But this time, this has a number over 10, which means this 10 is n. Okay? So if you wanted to think of it that way, all of these 10s are just n. Okay. And then if we look at the number on top, again, this number is telling us what? The distance. Okay. And if we look at all the changes, we have 1 over n, 2 over n, 3 over n, etc. Okay, what do you notice about all of those until they get to the very end? Okay, they are changing, and what would you say that... Okay, ignore the concept of n, just look at the numbers. Like if it's 1/10, 2/10, 3/10, all the way to 10/10, that means it's in what range? 1/10 to 10, so it's below 1, correct? So if we want to write this with only a distance of 1, would we do 1 to 2 or 0 to 1? 0 to 1. 1 to 2 would be outside of that range of 1/10 to 10 over 10. So this is the integral from 0 to 1. And then remember, every portion that's changing we can call x. So the function is what? Cosine of x. And we always end it with dx. So that is us taking that Riemann sum and converting it into an integral. But then the last question states, where did the 10 go? Okay. And what did we say the 10 represents? N. The 10 represents n. What's another word for n? The subintervals. Okay. So since 10 is in the subintervals, Does that have anything to do with f of x, the function? No. So it has nothing to do with f of x. So that's the reason why it's not in the integral, because it has nothing to do with cosine, our function. Okay, it's not saying that this is 10 cosine of x or 1/10 cosine of x. This is just how many rectangles we're going to draw from the interval of 0 to 1 under cosine to approximate that area. That's just number of rectangles. Okay. So the big thing to remember is that the larger n, the more accurate the area. Okay, so that goes back to even yesterday's notes with Riemann sum. We said the more rectangles, the more precise or the closer we get to the actual area.